who will tell us about three-dimensional minimal model program in positive characteristic. Hiromu?
Yes, thanks. So I think first, thank you very much for giving me the opportunity of this talk. And I think today's title is Modifiable Spaces in Positive Characteristic. So the main topic, okay, today we work over field, and mainly we are interested in the case when the base field is algebraic closed and the characteristic is positive, but I do not assume it for now. So the starting point is the MMP conjecture, which predicts that any algebraic variety is variational to either a minimum model or modifiable space. And today's topic is a modifiable space. So I would like to start by covering the definition of modifiable space. And before that, I need to define the definition of KLT singularities. So let us start with the definition of KLT singularities. We take a normal variety, and in this talk, variety means integral separated scheme, which is open type over K. So which is a usual definition, I think. Then we say that this is KLT, which is usually defined as X0 is KLT, and its definition is as follows. We impose two assumptions. First, we assume that some multiple of Kx is Cartier, and the second condition looks complicated than the first one. So we take arbitrary variation, projective variation morphism from normal variety. Then we can define E, which is a G exceptional Q divisor. And if we take such any partial morphism, we can define E. Then the condition is to assume that any coefficient of E is greater than -1. This is a definition of KLT. If you are not familiar with KLT singularities, then I think this implication might be helpful. At least if X is smooth, then it is KLT.
I'm sorry, and what is 0? So you say that x is KLT if x comma 0 is KLT. What is 0?
Oh, usually this is X delta, which is divisor, Q divisor.
But there is no divisor in your definition, right?
Yeah. So just you can ignore this part. So usually, I think many people define KLT singularity for pair, but today I only use this X, the case when delta is equal to 0. So if this
Okay.
is
Thanks.
yeah. Please ignore this one. Okay, so I have defined the KLT singularity. So now I would like to give the definition of modifiable spaces. So we take a KLT variety. So by definition, this is at least normal variety. And we say that a morphism is a modifiable space. I just write it by MFS. And we say that morphism is modifiable space if these four conditions hold. First, this morphism is assumed to be a projective morphism, and both of them are normal varieties. And we assume that push forward of OX is equal to push OB. The push forward of structure sheaf is structure sheaf. The second assumption, minus K is ample relatively, and the dimension strictly drops, and the relative Picard number is equal to 1. So let me add some remarks on this definition. First, we allow the case when the dimension is equal to 0. And in this case, by definition, x is projective from the first condition. X to B is projective morphism, so x is projective over spec K. And the minus Kx is ample, which follows from the second assumption. And Picard number of x is equal to 1, which follows from the first condition. So this is KRT Fano variety of Picard number 1. So as I said, modifiable space is one of the end product of mirror model program, which is now just a conjecture. But so we would like to know many properties for group modifiable spaces. So I now summarize such properties in characteristic 0. So here we assume that characteristic of K is equal to 0. And for simplicity, let me assume that K is algebraic closed. And we take a KRT variety and take a modifiable space from X. Then I would like to show you 3 properties as follows. In the first property, I consider general fibers. So it is KRT and minus K is ample. So general fiber of modifiable spaces are KRT Fano varieties. This is basically follows from Bertini theorem with some arguments. As a second property, the higher direct image of the structure shift is vanishing. This is
very sorry. And what kind of Bertini do we need here? I think there
Bertini,
are lots of problems with Bertini theorems in positive characteristic. So
yes. So actually, so Bertini for this one is a Bertini for base point free divisors, which fails in positive characteristic. So at least this argument needs a characteristic 0 case, 0 assumption. So this is characteristic 0. So we take a base point free divisor, then which satisfies.
sorry. Yeah, it's still characteristic 0. I didn't notice it. Yeah, sorry.
Yeah. I'm assuming that the characteristic is equal to 0. Yeah.
Do you mean that you use Bertini and argue by induction in dimension of B?
Yes. I think so. Yeah. We cut out finite many times. So we apply finite many times. Yes. So in that sense, we apply induction. Yeah. Okay, I think I have explained up to B, maybe. So so this is vanishing because of Kant-Fibeck vanishing. Then the first property A is about the fibers, general fibers, and the third property is about the base. So the base is KRT if the total space is Q factorial. And in many definitions, modifiable spaces is actually assumed to be Q factorial. So this is basically sometimes, some authors actually assume this condition. So, and this is actually a mild condition.
And the base is Q factorial as well, right? In this case.
Yes. In that case, yes. B is Q factorial as well. Yes. Okay, so now I want to switch to the situation in positive characteristic. So the first naive question is to ask whether these properties hold in positive characteristic. Do the same properties hold in characteristic P or not? Then as for the
And
first,
what is assumption on the field? Is it algebraically closed or you allow finite fields?
okay, so let me assume that, okay, then let me assume that everything is algebraic closed. And so, okay, so the answer for these questions. So for the first question, the answer is no. I mean that even if we have a modifiable space in positive characteristic, general fiber could be could violate these properties. Then the second property, the vanishing of the higher direct image, this is also negative, which means that for some example in positive characteristic, this is could be non-vanishing. As for the third property, so which is asks whether the base is character or not, the answer is again no. So everything is false for each question. So even for algebraic closed field, we have negative answers. Now I'd like to give some examples to assure these negative answers. So I mean, I will show you some counter examples. So I'd like to start with question A, which maybe I should show you this page. The question was, the property was this one. We have more fiber space, then general fiber as a KLT funnel. So maybe the simple counter example is as follows. We work over algebraic closed field of characteristic 2. Then we first take a three-dimensional affine space, which is B, this is a base space, and we take X to be hypersurface inside this direct product. We first consider this direct product and T and X are coordinates like this. Then we take this equation. Then we can check that this is a morphoidal space. For example, this is actually smooth for fault. This can be proven by Jacobian criterion. But any fiber, I mean more precisely geometric fiber, is not reduced. So for example, if we take a fiber.
And P is equal to 2 is not essential here. Or is it essential?
No, I think it's essential because you prove non-reducedness by basically taking derivatives. And
So
by X.
I see. I see.
I think that results of this sort can be considered possible only for small characteristic. If it's small with respect to dimension, right?
Yeah, basically, I think so. At least this
So
construction. Yeah. Okay, so let me give you.
But I'm sorry. Why can't you take Fermat type hypersurface in characteristic P for any P? Just some Ti xi to the power P. What's the difference?
So you mean replace this by P?
Yeah.
So I want to assume that something is a funnel.
Okay.
Yeah. So because of P2, so must be this should be bounded.
But if you increase the dimension.
Yeah, exactly. So it is exactly in the next page. So
Good.
okay, so okay. Let me explain the details on this part. So we take a cross point, and consider the fiber over that. So I now assume that each AI is an element of K. Then the fiber is the approach of this is a conic curve, which is obtained by replacing this T by A. So T becomes A. So the equation becomes like this. But in characteristic 2, this is not reduced because we have this equation.
And just small irrelevant question: why do you need the base to be three-dimensional? You just wanted.
So yeah, just to make this symmetric. So look, just make this beautiful. So I think we can drop some. Maybe I think.
Suppose that you just make it one-dimensional and delete the coefficients at x1 and x2 and leave only the coefficient t at x0 squared.
So you mean erase both of them? I think we can erase one of them, but if we erase both of them, then this becomes x1 plus x2 squared, then which is not smooth. So we can erase one of them, but we erase two of them, then I think it's too much.
I see.
Yeah. So I think it is easy to make this two, but I think one is we need some modification. At least this construction needs such. Yeah, such a restriction. Anyway, so this is a proof for this one, and I didn't give the detail for any other conditions for morphic spaces. And as mentioned before, so this example can be generalized to any characteristic if the dimension becomes larger, in the sense that if we replace every two appearing here, become is replaced by p, and 3 is replaced by p plus 1, then everything is automatic. Okay, so this is, so basically, so general fiber becomes quite bad in positive characteristic. So this is what I wanted to mention in question A. So now I want to go to question B. Okay, it might be better. Yeah, so okay, let us go back to the original page, input character 0. So in character 0, we have this vanishing, but as I said, there is a counterexample input per characteristic, which is written here. I added some information here. So if K is algebraic closed and characteristic is 2 or 3, then there is this counterexample as follows. And R1 is not vanishing. Such examples are constructed by 3 people, including me, and all example is relative to dimension 2. And such counterexample only found in small characteristic, which means which I now want to write down as related topics. We do not know whether similar counterexample exists in larger characteristic. I mean, even in characteristic 5, we do not know. So yeah, this is open. And maybe, so as another question, so modifiable space is basically similar to Fano variety. For example, if current number is if B is a point, then it is Kerti Fano. So we can ask similar question for smooth Fano variety, but which is also an open problem, which means that if X is smooth Fano variety of positive characteristic, then we do not know whether the higher cohomology of the structure sheaf is vanishing or not. This is known up to dimension 3. This is proved by Shepard Baron and Kawakami.
And also,
No.
can you what about this, say, direct image counterexamples? So we don't know anything for surfaces. Any examples of such bad behavior for surfaces, right?
Sorry, we don't have. Sorry, I don't hear you. Sorry.
So you said that in all the examples of bad behavior for property B, the dimension of the variety is minus the dimension of the base equals 2. So this means that these bad examples cannot be constructed for surfaces. But do we know something positive in the surface case?
So you are asking some positive results for.
Well, I mean, so you said that no examples like this are known for, in particular, for surfaces. On the other hand, do we know that they are really impossible for surfaces, or we just don't know such examples yet?
I'm really sorry. I think I do not understand the question. So,
just the short form of the question: what do we know for surfaces concerning property B?
So surface means dimension of X is 2.
Dimension X is 2. Yeah.
I see. For if assume that if dimension of X is equal to 2, then this is okay. This is vanishing. So
we know vanishing here.
Yeah, we know vanishing and assuming the base freeze is actually closed.
I see. Thank you.
Yeah. So yeah, if you just know about the total dimension, then I think if dimension is equal to 2, then everything is okay. So I mean, vanishing is actually okay. And the dimension is equal to 3, then yeah, this example and this example actually, this counter example can be constructed for total dimension 3. So dimension 2 is okay, but the dimension 3 is not okay. Okay, so now I want to add some details on my example. So there are 2 steps. What we first do is as follows. We take a Azure closed field of characters 2 or 3. Then we take the function field of P1 over K. This is imperfect field denoted by F. Then we construct some KLT depth surface over this imperfect field. Here, the depth means 2-dimensional and minus K example. And corresponding to this non-vanishing, we want to find KLT depth surface with this property. This is the first step. The second step is, in a sense, routine. We have some variety over this field. Then we can spread out Y over open subset over PA1. So which means that we can find a morphism with this Cartesian product by killing denominator, defining this variety. Then we can check that this is more fiber space. So this is the outline of the construction. So in this sense, this is almost automatic. So the essential part is the first step. So now I'd like to concentrate on the first step. Okay, so okay, in this term, less information is added, but the situation is a little bit generalized. So we take a imperfect field of characters 2 or 3. This means imperfect. Then we can find a pathological example, which means that Y is a projective character surface over F, and minus K is ample, and the Picard number is equal to 1, and H1 OX is non-zero.
So just in case, do I get it right that if you pass to the algebraic closure, then only the second property may break down in your theory, in this theorem?
Sorry, we assume that this holds. Then third
Just if we consider this surface over the algebraic closure of your field.
you mean we will go to the base change?
Yeah. Then apparently, something wrong may happen with the Picard rank, but the other two properties will, of course, be still there.
Yes, and this will break up. For example, normality
Chaotic
could.
singularities.
Yeah. Even like this could be non-reduced, so main property could break up.
This is maybe even more interesting.
Yeah, so it's base change is a very very drastic operation in positive characteristic.
Thank you. Life is even worse than I could imagine.
And so this is in a sense, so theorem 1 is in a sense a core of this construction, but theorem 1 almost implied by theorem 2. Now we have a look in the next page. So again, the condition of the field is the same. So we take a field which is imperfect and the characteristic is 2 or 3. Then we can find morphism satisfying these 4 properties. First, this C is a curve which is regular projective curve whose canonical divisor is trivial. So if the base field is algebraic closed, this means that C is an elliptic curve, but this is not smooth. I mean, after taking the base change, this becomes non-smooth. So this is now regular, but after taking the base change, this becomes non-regular. This is quite typical of an imperfect field. Then the second property is nice, which means that this is a pure bundle in the usual sense. I mean, this is the projective vector bundle associated to a lag2 vector bundle on C. So this F is in particular smooth morphism. The third property looks complicated, but this is similar to scarcity, which is weaker than scarcity, but in partial geometry, this is quite common. At least let me mention that. And this condition is related to discarity and final condition. And the final condition is to assume that Z has a negative section. And I think now I should mention what is the relation between Z and Y. So we have negative curve gamma, so we can contract gamma, which is nothing but the contraction from Z to Y. This is a contraction. Partial contraction of gamma. So, and okay, so as another remark, I should mention why this condition holds from 7 to. Let me mention about it. So we've tried to compute what is H1 of Y. This is non-trivial but easy. Because for Bayesian morphism for surfaces satisfies count Fourier expansion, even in positive characteristic or even by box field. So we get this condition from KLT condition. Then this is also isomorphic to the H1 or C. This is easy because from Z to C is a P1 bundle. And finally, this is easy to see that non-zero because this is a curve which looks like elliptic. So we can just use triviality of mechanical divisor and cellularity. Okay, so now I think if we assume that theorem 2 is okay, then theorem 1 should be okay.
But the surface you construct like this, it's not geometrically normal, right?
Not geometrically normal. Yes,
Okay.
it's not geometrically normal. Yes.
And the
so
singular locus is over the singular point of this, or over the singular locus of this regular non-smooth curve.
Yeah,
That will
exactly. So actually, after taking the base change of this curve, this becomes capital cubic curve. So along that fiber, that is not smooth. The base change of that is not smooth.
Thank you.
Hiromu, and so I see that you use theorem 2 to use theorem 1. And can you show the previous page just before theorem 1? So theorem 1 was used to construct an example.
Yes, here.
Yes, but I'm just missing. It seems to me that there is a little gap between this example and theorem 1. So you to use theorem 1 for this example, you need your surface y to be it's going to be over f, not over k.
Yes. First we fix either cross field and we take imperfect field. Over that we take y.
I see. And then maybe one more question. So you are saying that all these three properties like A, B, and C, they are all going to fail in general in positive characteristic. So what if you allow positive characteristic but require that the field is like perfect or algebraically closed? Are they also going to fail?
Yes. So as I said, so even larger closed field, this question will fail.
But our current, what are we doing at the moment? Are we constructing counterexample? What are you doing at the moment? Are you constructing counterexamples to these properties over non-perfect fields?
No. To find counterexample over either closed field, I use surface over no imperfect field. Because for example, so this.
Yeah, so
is-
you just say that a surface over such a field is more or less the same as a threefold.
Yeah, this is a generic
over
fiber.
K fibered into surfaces.
So this is so for 3 dimension to 1 dimension. This is usual axial closed field A1, and it's open subset, and this is 3/4. Then generic fiber.
Yeah, I see.
Okay.
Yeah, so you just in fact then say that.
Generic point and generic fiber.
Yeah, I got it. Thank you.
Yeah. Okay, so yes. So we now want to. Okay, so one was the goal of the counterexample, but now as I explained, so the problem is reduced to construct example written here. So now I'd like to give some construction, but I do not give the complete details. So I omit some details. So as I written here, characteristic is 2 or 3, but let me concentrate on the case when p is equal to 3. And also for simplicity, let me assume that f is equal to this field. K is the closed field of characteristic 3, and we take the function field of P1 over K. Then in this case, we first define C to be this cubic curve inside P2. And this is the generic fiber over case elliptic fibration. So which only exists in characteristic 2 or 3, which is the reason why I need to assume that the characteristic is 2 or 3. So also in characteristic 2, I use similar equation. So we start with cubic curve. And we take a rational point of C. So 0, 1, 0, then this is okay. So this is rational point of C. Then we see that this cohomology is not vanishing. This follows from cell duality and the triviality of canonical divisor. As I said, this is a cubic curve, so canonical divisor is trivial. So we apply cell duality. Then this becomes H0 of H0 C Kc plus Q. But Kc is trivial, so this is non-zero. As we know that this is non-zero, we can pick a non-zero element, which corresponds to a vector bundle of rank 2, because we can see that this is some x1 or something. Then we take Z to be pure bundle associated to this vector bundle. Okay, so of course we need to check many details to prove this theorem actually. Then, but let me omit it for the details.
And why do you need to take non-zero alpha? Why couldn't you take just the direct sum? What would fail?
Then so if we take this kind of element, then the resulting P1 bundle has this kind of property. So we have Z, which is a P1 bundle, and we have C. Then we have some section and other multi-section, which is maybe denoted by C minus, which has P21 purely inseparable cover. So this is actually crucial in the construction. So if we just retake split zero element, then this is C minus is just a usual section, then it does not produce anything interesting. So this is, yeah, we can find, I think one of the reasons is this such multi-section.
So it's not a section, it's a multi-section, right?
Yeah, this is not a section. This is theoretically one-to-one, but yeah, but it's not.
So,
Yeah,
so in other words, you have a section after purely inseparable base change, right?
Yes, exactly. After change, for example, take the base change by this curve, then we have section. Yeah, exactly.
Okay,
This
thanks.
yeah. This kind of construction is basically maybe from Renault to construct counterexample to the Kodai vanishing, the original counterexample of the Kodai vanishing. I think it is the first time using this kind of vector bond. Anyway, so now I explained what is the construction of the counterexample. So let me briefly summarize what it was the construction. So because the construction looks complicated. Thus, we start with a closed field of characteristic 2 or 3, and we take a field like this. Then by theorem 1, which follows from theorem 2, then we can find pathological projective characteristic surface. Then we spread, sorry. Then we spread y over some open subset of A1, then we can find what we want. And this is generic point and this is generic fiber. And we know this non-vanishing. Then flat base change theorem implies this non-vanishing because from here to here, we get the some tensor product. So if left is non-zero, then right is non-zero.
Actually, I think you don't really need a flat base change here. Just your B is affine, and therefore H1 is just H0 of the first direct image.
Okay,
Right.
okay, thank you.
And can you extend this counterexample to the case when B is proper?
So far, I do not know. Yes, I do not know. So yeah, what I have considered is to take some convertication and running Mima model program, but I do not know. I do not see it can be doable or not. Yeah, so yeah, I do not know.
Thanks.
Okay, so this finishes the explanation of counterexample on B. And let me add some remarks on the other example. So this example is from my paper. So there are also two papers. So the first example is actually given by Schreier. He constructed canonical diverse surfaces over any imperfect field of characteristic 2, which satisfies this property. And I did not explain what is canonical, but at least for the surface case, even by impact field, this is equal to KT plus Einstein. So if you are not so familiar with this notion, then just consider KT plus Einstein.
Is it the same as Duval?
Oh, sorry, it's the same as dual. So, sorry.
Is it the same as Duval singularities?
Oh, Duval. Duval. So which means some equation, explicit equation you are talking about.
Maybe.
So yeah, I do not know what is the definition of Duval singularities in over imperfect field. Maybe other closed field, it's Duval.
And I think that in positive characteristic, even over algebraic closed field, the equations are not so explicit as they are in characteristic 0 with Duval singularities.
Yeah, you are right. You are right.
I think that Claudia explained us maybe several months ago that in some characteristics, some of the Duval singularities have moduli or something.
Yeah, and the canonical surface singularities are precisely the rational double points. So I think that should be divided Petzos.
And you have more equations in small characteristics.
Yeah. But you have equations for all of the cases.
Okay, so okay, then okay, can I go to the next question? C. So
And I'm sorry, can I ask what are the degrees of these del Pezzo surfaces in these examples?
Degree. Oh, you mean K square?
Yeah.
So I don't remember the degree of this one, but if I remember correctly, this example K square is 1 or 2. So he contrasted 2 examples. So 1 and 2 is he has counter example in degree 2 and 1. It's 1 and 2, but yeah, I don't remember this one. Sorry.
And in your example?
On this example, so minus k is not criteria, so I think it should be fractional. So I did not remember I have confused it or not. So sorry. Sorry.
Okay, thanks.
And can I ask one more thing about those examples? Are they all geometrically non-normal? Is it even possible to write down a geometrically normal example where this phenomenon happens?
So this is, as you mentioned, I think this is, I do not think that this is, I think this comes from Z to Y, and this is not geometrically normal. And this is also not geometrically normal because we have, we have this picture like this. The contraction, this is a contraction of gamma, and this is non-smooth locus. So this has non-smooth locus of one dimension. So this is not geometrically normal. And for these cases, it's impossible to find geometrically. Actually, these are geometrically non-normal because if we have this result, if a canonical Hilbert surface, then if we take the base change and take reduced structure and further we take normalization, then this is of Hilbert type, which means which at least imply the first cohomology is vanishing.
Thank you.
So yeah, it's impossible to find such example for the canonical.
Sorry, I missed the very last point. So you are explaining that an example like Schroer and Medlock, they must be non-normal over the closure, right? They must be geometrically.
Yes, they must be geometrically non-normal.
So because if they were geometrically normal, then in this base change, after this base change, you will need no reduction and no normalization.
Yeah.
And then
it must vanish.
All homology groups will be the same. Yeah, thank you.
Yeah, exactly. Yeah. So there's a chance to find such example for chaotic case, but for canonical case, it's impossible to find.
Thank you.
Okay, so now let me go to the next question, C. And recall that what was the question? We have a Q-factorial charity variety, and we take a modifiable space from X. Then the question is asks whether base space is charity or not. And as I said, the answer is negative. There are two types. Oh, I forgot what's the name. So for small characteristic, I give contact example. The dimension is from 4 dimensional to 3 dimensional. For the characteristic at least 5, the dimension is the base is 3 dimensional and total space is P plus 3, which is constructed by Bernasconi. And the construction is totally different. So in my construction, this one, we use the P1 bundle. I have explained in the question B. And I need to modify some things. So, and I think it's minor parts. So I would like to explain the second construction here. This construction uses wild quotient, which means that quotient by, for example, Z of PZ or something. And actually, so in this construction, we use Z of PZ. Let me explain the details about that. So the group G is Z of PZ, as I said. We take two varieties on which G acts. On the first variety, which is P1 to B, I'm sorry, everything is of either closed field or positive characteristic. And its action is the cyclic permutation, alpha 1, alpha 2, alpha p, where each alpha I is an element of P1. Then this is cyclic permutation, alpha 2, alpha 3, alpha p, and the last component is alpha 1. And for the second action, let me assume that P is at least 3. So this is the irreducible representation, which just means that by linear algebra, the action is given by Jordan form. So this is order is equal to P. So this is the action given by G. More precisely, the generator of G acts by this one to the 3-dimensional vector space.
Did you mean indecomposable? I mean, because you have a fixed vector.
Okay, sorry.
Sorry for that.
Sorry.
Yeah.
Okay, so sorry, thank you. Okay, then, what we would do is to consider this square diagram. And first, so both horizontal is the quotient, and this particular arrow is G equivalent, and each of them has G action. And this one is nothing but this one. And this one is a diagonal action, as I explained. So this one has G action like this, and this one also has action. And this is a second projection. So this is G equivalent. Then taking quotient, then we get commutative square. And this resulting particular arrow is a morphoidal space, which gives a counterexample. So this is the total space, and this is the base space. So we need to check the definition of morphoidal spaces, but I think the crucial part is to check that X is KRT, but P is not KRT. So let me briefly explain how to prove it. So
I'm sorry, and can you replace P1 to the power P by the P dimensional projective space?
to be honest, I'm not so familiar with this example, but I think so. The key part is to use this theorem, so which is G. G is the same, and we consider action to the vector space. So we need linear action. So this action should be locally written as action of G, action by G by linear algebra. But if I remember correctly, if we replace this one by P minus one dimension projective space, I guess.
Right.
Yeah. But I do not think, if I remember correctly, it was hard to apply this term. But I'm not so. It's at least I have considered it once, but yeah.
Okay, thank you.
Yeah. Okay, so we work on larger cross field and G is as before, Z of PZ. We take a finite dimensional vector space with G action, so finite dimensional representation. Then this direct sum is just a decomposition to indecomposable representation, which means that each dimension is from 1 to P, and action is given by this Jordan form. Under this notation, we introduce invariant, which is a non-negative integer. For each vi, we consider this number, which is dimension minus times dimension minus 1, which is even, so this is integer, and we take the sum of them. Then Yasuda's theorem states that this quotient variety satisfies this equivalence under this very mild condition. Okay, so let me just explain the easiest case, which is this one appearing here. And as I said, this is non-KLT. Let us check that this is actually non-KLT by this Yasuda's theorem. In this case, dv, this is already indecomposable, so this direct sum does not appear. Sigma is not here, so this is just 3 times 3 minus 1 over 2. And of course, this is 3. And here, we use the assumption that P is at least 5 in the, which is written here. This assumption comes from here.
So this is an extremely rare case when some construction gives a worse result in large characteristic than in small characteristic.
Yes, I think this construction is yeah, very good, and it's much simpler than mine. And yeah, now happily, I think this fills all characteristics. So yeah, this example is very interesting. And let me add a final remark, which is an open problem related to this one. So let me assume that the base field is Azure closed. Then I think the smallest dimension is 4, giving counter example. So the natural question is, what is the what is the smallest counter example? So in terms of dimension, as I said, if the dimension is equal to 2, then we can, it's impossible to find counter example. So only the remaining case is dimension 3. And if the possibility for dimension of the base is 2 or 1 or 0, but if 1 or 0, then of course B is smooth. So only the remaining case is 3 and 2. So the question is, remaining question is this one. And for any prime, we do not have any answer. So usually, if characteristic is large, then the problem is easy, but we don't know. And as a related result, in this setting, if P is at least 7, then we know that P has rational singularities. For the surface case, clarity implies rational, so this is a weak evidence supporting this implication in this case, but we have any other evidence so far. So now I think I would like to stop here. Thank you very much.
Thanks a lot. So, any questions?
How about first two problems? Suppose a characteristic is sufficiently big. Do you expect a positive result, a positive answer?
Yeah, so general fiber
A and
should
B.
be, yeah. So, yeah, basically, if P is very, very large, a fixed dimension, and depending on dimension, if P is very large, then I hope that everything is okay. And as a partial result, for example, if X is dimension 3, and P is 1 dimension, and P is at least, let me check. So at least 11, then it, yes, and I think this is, even for this case, general we do not know, but if this is regular, then it is known that this is smooth. Some weaker results hold, but I think for the general, even for this case, I think question is open.
So I don't get it. Who is smooth in this situation? B?
Sorry. General fiber.
General
X is regular, then general fiber is smooth. Sorry. Yeah, I hope it, but I think there are less evidence so far.
Other questions? Maybe, so I have a question which comes in two parts. So the first is, so we see that if you just assume that a variety which you start from is KLT, then life is hard, life is tough. Suppose that it's not KLT, but say terminal. Does life become better in this case?
So
It sounds like pretty
I think-
natural to assume that a variety is terminal.
Yeah, for example, if this might be one example on such phenomenon, which means that this is terminal, then I think if we consider the general fiber, then and this is just smooth, then we get something good. But yeah, and maybe so in general, I think there is different. I think KLT is basically unbounded, and the epsilon KLT might be similar to bounded case. So, for example, so if for smooth variety, smooth fan variety, I think this should hold for if X is epsilon KLT. At least if we believe BAV conjecture over positive characteristic or mixed characteristic. So in this sense, terminal means I think might help in the general theory, and KLT might be too strong to
I
practice.
don't get it.
Yeah.
I don't understand what you are saying. So every KLT singularity is epsilon KLT for some epsilon, right?
Yeah,
something
but what I want to say is P is big means this big means it depends on epsilon. So we fix epsilon, then depending on that we can find the lower bound for P, and the dimension is also fixed. Epsilon the dimension is fixed, then I think if P is very, very large, then smooth fan variety should satisfy this property.
So in particular, this predicts that for terminal singularities,
Terminal case should be
for large enough P.
Terminal and canonical should be okay.
But however, many of your examples work for many of your counterexamples. You have counterexamples for just for small p. So back here, do we know or do we expect that, say, in characteristic 2, with terminal singularities, such a vanishing theorem holds?
Sorry, characteristic 2 and the dimension. What is dimension?
Well, I don't know. Say dimension 3 and terminal singularities.
Nobody knows.
It sounds but at least there exists counterexample for canonical singularity case, if I remember correctly.
So terminal is just the correct question to ask because it's the next.
Yeah, terminal threefold is still open problem, but I think canonical fan threefold, then there is this counterexample, if I remember correctly. So it's very for terminal case maybe it's still alive, but I have no idea it should hold or not.
I see. And another question. So as far as I got from your counterexamples, there are many problems caused by Gebhardt pointed out this several times that many problems are come from geometric non-normality of a generic fiber of a vibration, and so KLT singularities of the ambient space is compatible with this geometric non-normality. Suppose that you can you in principle have some other class of singularities which is more restricted than KLT, such that these geometric non-normality effects are not possible.
I see. So
maybe KLT is too large class to consider.
Yes, but basically general fiber is, maybe I think the first example might be, I think even if everything is smooth, I think.
Here.
Yeah, so I think singularity could be very bad. I think non-reduced is, I think, worst case. So yeah, I have no idea.
So there's no way to restrict singularities a little bit more so that. I see. Thank you.
Yeah, I have no idea. Yeah.
Okay, any other questions? If no, let's think